Alright, so we said earlier that the position of an electron in an atom is really important in terms of determining its energy, right? So we know that as the separation distance, and r here is the separation distance, of an electron from the nucleus increases, then what happens is the relative kinetic energy of that electron also tends to increase. And we know that separation distance is associated with a decrease in the effective nuclear charge. And because there's a decrease in the effective nuclear charge, right, because now the electron is further away from the nucleus, this implies that the force of attraction also decreases. And if there's less force of attraction between an electron and the positive nucleus, then as a result, the kinetic energy of the electron is higher, right? So now the electron isn't being tethered by the nucleus. Okay, so this is really a notion. You can think about this in the opposite scenario. So vice versa, as the separation distance decreases, electrons are closer to the nucleus, and we know that the force of attraction between two charges is going to be a lot higher, right? Now, using this notion, it's very important to understand the energies of electrons, and in order to do that, we need to determine the position of the electron. Well, how do we determine the position of the electron? Now, we looked at how to construct an orbital diagram, but how do I pinpoint an electron's relative position within an atom? If you're looking at an electron's position, we use something called quantum numbers. A quantum numbers act as an electron address book. And really, this notion of an electron address book, it tells you exactly what the electron is relative to its shell, subshell, and orbital, right? So we're going to be looking at 4 different quantum numbers to demonstrate that. And the 4 quantum numbers is n, the shell number. So this one you've already kind of seen. N is the shell number. We're also going to use L, which is the subshell number. ML, which is the orbital number, and MS, which is the spin number. Okay, now these guys are also given different names. You can also consider this, all right, the primary quantum number, the primary quantum number, the secondary quantum number, the tertiary, making mistakes today, the tertiary quantum number, and the quaternary quantum number. So you can also consider them in this format, right? The other names that these guys are usually given, right? This is called the angular momentum quantum number. But I honestly think it's a lot easier just to look at it this way. This is the angular momentum quantum number. Right? This is called the magnetic quantum number. This is called the spin number. Okay, so this is basically called the same, right? Now, we'll just look at it this way, so it's just easier for us. Okay, so we'll just look at it in this format. Okay, so let's start with the shell number here. So, the primary quantum number, also known as the shell number, right? This basically tells us which shell a particular electron occupying an atom is found, right? This is one of the hallmark features of the quantum mechanical model, is that we need to look at the position of each electron, because the position of each electron is going to be slightly different than the rest, right? So the shell number tells us which shell the particular electron will occupy. And this one's pretty straightforward, right? The valence shell is basically going to be the furthest shell, or the outermost shell. Outermost or furthest shell from the nucleus. And because this is the furthest shell from the nucleus, we can understand that it has the greatest separation distance. Okay, so it has the greatest separation distance, so that means that R value is going to be the maximum for that atom, right? So the R value would be maximum, as a result, the kinetic energy of that electron will be the highest. So that's why we look at the valence shell, because the electrons in the valence shell, also known as the valence electrons, they have the highest energy. And we're going to talk about how having high amounts of energy means that electrons will collide with other electrons, and usually there's going to be some sort of chemical reaction that takes place. Okay, so that's your shell number, and then the next quantum number that we're going to be looking at here is something called your subshell number. Okay, so the second quantum number is called the subshell number, also known as your angular momentum quantum number, but I'd prefer you guys to take a look at this as your subshell number. We're going to use L for our subshell number. Now L here has a series of values, and the values of L will actually tell us what type of subshell we have. So these are some values of L. This is the type of subshell, so we can have values of 0, 1, 2, 3, right? And when L is equal to 0, this indicates we have an S subshell. When L is equal to 1, we have a P subshell. When L is equal to 2, we have a D subshell. And when L is equal to 3, we have an F subshell. Okay, so it tells us what kind of subshell we would expect. Each of these subshells are composed of different orbitals, right? S subshells are made up of S orbitals, P subshells are made up of P orbitals, and so forth. Now, within an electron, so the subshell number tells us what type of subshell a particular electron can be found in, right? So we understand that the energy of the subshells are as follows, right? So the P subshell has more energy than the S subshell because the P subshell is further away from the nucleus within a given shell, right? Remember that subshells are found in a given shell, and so forth. The D subshell has more energy than the P subshell, and the F subshell has more energy than the D subshell. So using this notion, we can actually figure out a particular subshell in a given shell, and the highest energy subshell in a given shell is indicated by this equation. N is equal to, not N, but L is equal to N minus 1, okay? Where L is the highest energy subshell in a given shell. So in a given shell number, right? So technically what this really means is that within a given shell number, L can take on values from 0, 1, all the way to N minus 1. Okay? So we always start at, well, we should say 0 to N minus 1. Right? Because they'll continue on. But L can take values from 0 all the way to N minus 1. Right? In some cases, N minus 1 is 0, so there's only one given subshell. So N minus 1 is the highest energy subshell within a given shell. So we're talking about L, the subshell number, and we had this chart here where if L took on these particular values, then it represents a particular subshell. So if L is equal to 0, we have an S subshell. When L is equal to 1, we have a P subshell. When L is equal to 2, we have a D subshell. When L is equal to 3, we have an F subshell. We also stated that the subshells occur within a given shell, and the highest energy subshell number is N minus 1. So we know that L can take on values from 0 all the way to N minus 1. And N minus 1 is the highest energy subshell in a given shell. Right, so you want to recall that when we're looking at the quantum mechanical model, electrons are organized in orbitals. Orbitals are organized in subshells, and subshells are organized in shells. Right? So we looked at the primary quantum number, and the primary quantum number is the shell number, so we're actually going backwards here. Right? So we're going from broad to more specific. The secondary quantum number tells us the subshell. Okay? So having said this, let's say we had the third shell number. So we're in the third shell. Let's look at all the possible subshells that can exist. So L can take on values from 0 it can also take on 1, and n minus 1 here is basically 3 minus 1, which is 2. So L can take on values from 0, 1, and 2. And the highest energy subshell is L is equal to 2. What does that mean? Well, in this case, when n is equal to 3 and L is equal to 0, this is the third energy level. L is equal to 0 is the S subshell. This indicates the 3S subshell. Okay, so that's the 3S subshell. It's the S subshell in the third energy level. When n is equal to 3 and L is equal to 1, when L is equal to 1, this is the P subshell. So collectively, this is the 3P subshell. When n is equal to 3 and L is equal to 2, this indicates the 3D subshell. Okay, so usually how we write these subshells is we'll write a subshell as n and L. Okay, n is the shell number and L is the subshell number. Okay, so this is how we can represent a representation of subshells. Okay, so this will tell us what potential subshells can exist in each given shell, right? So another example here, if n is equal to 4, then the fourth energy level, L can take on values from 0 all the way to n minus 1. Well, n minus 1 here is 4 minus 1, which is 3, right? And so L can take on values of 0, 1, 2, and 3, and the highest energy level is the third energy level. So when n is equal to 4 and L is equal to 0, this indicates the 4S subshell. When n is equal to 4 and L is equal to 1, this indicates the 4P subshell. When n is equal to 4 and L is equal to 2, this indicates the 4D subshell. And when n is equal to 4 and L is equal to 3, this indicates the 4F subshell. Okay, so that's literally how that would work, right? So it's a really useful way of kind of quantifying these subshells. Okay, so we looked at the shell number and looked at the subshell number L. Let's take a look at the third quantum number, the tertiary quantum number, which is called the orbital quantum number, ML. Okay, so this is the orbital quantum number. Okay, this is just the easier way to remember its name. And basically, ML, it tells us which orbital an electron is found in a particular subshell. So we know that subshells are combinations of orbitals, right? So going back to our representation of the quantum mechanical model, electrons are found in orbitals. Orbitals can hold up to a maximum of 2 electrons. It can be empty, half-filled, or spin-paired. Orbitals come together to form subshells. So subshells contain particular orbitals, right? Contain multiple orbitals. And subshells form energy shells, or electron shells. Okay. Now, we looked at the primary quantum number, which indicates electron shells. The secondary quantum number indicates the type of subshell the electron's found in. The third quantum number will represent which orbital particularly will be found, where will the electron be found in within a subshell, right? Now, in this case, we can understand that the orbital quantum number, the third quantum number, is dependent on the subshell number, right? So to calculate ML, ML can take on values from negative L to positive L. So this is the representation of ML. So ML is dependent on L, right? So for instance, if L is equal to 2, recall that our chart for L is equal to 2, this indicates a D subshell. Okay? If L is equal to 2, ML can take on values from negative L to positive L, and they're a series of natural numbers, right? So L is going to belong to a series of natural numbers, right? Or basically, whole numbers or integers, series of whole numbers, right? And they're going to be a series of integers, right? And in this case, ML can take on values from negative 2, negative 1, 0, positive 1, and positive 2. So it goes from negative 2 or negative L to positive L. Okay? And this represents each of the orbitals that's found in the D subshell. Now you can notice that there is basically 1, 2, 3, 4, 5 numbers. This indicates that there is 5 d orbitals. Each of these numbers represents the name of a d orbital. There's 5 d orbitals in a d subshell. So this can actually tell us how many orbitals we find. And now in the d subshell, so this is the d subshell, each of these d orbitals, the tertiary quantum number actually labels it. This is the -2 orbital, the -1 orbital, sorry about that, -1 orbital, this is 0 orbital, first orbital, and second orbital. Okay, so it actually labels the orbitals in the d subshell. Now each subshell is also demonstrated by a certain energy number, right? So let's say we're looking at n is equal to 2. Well, in the second energy level, L can take on two values because the highest energy level is n minus 1, right? So in this case, L is equal to 2 minus 1. So the highest energy level here for the subshell is going to be 1, right? So when n is equal to 2 and L is equal to 0, this indicates the 2s subshell. When n is equal to 2 and L is equal to 1, this represents the 2p subshell. Okay, let's take a look at the 2p subshell. If you're looking at the 2p subshell, if L is equal to 1, if we look at the tertiary quantum number, ML can be -1, 0, and +1. Because there's three values here, this tells us that there's 3 p orbitals in the p subshell. Right, and you can actually label them. Instead of writing them as px, py, pz, we can write this as -1, 0, and +1. So the ML tells us which orbital we're actually looking at in a subshell. So it's really useful, right? And basically the value is going to be dependent on the second quantum number. Okay, so we looked at the shell number, the primary quantum number, the subshell number, the secondary quantum number, the orbital number, which is the tertiary quantum number, and the fourth quantum number is called the magnetic spin quantum number. This actually gauges the orbitals, right? And basically this quantum number we're going to abbreviate as MS. And basically the magnetic spin quantum number will tell us whether the orbital is spin paired or half-filled. Now we can also indicate empty orbitals as well. An empty orbital actually has no value of MS, right? It's not applicable. So there won't be a value of MS, so that indicates it's an empty orbital. But a half-filled orbital can have an MS value of a single value, right? So here's a half-filled orbital. And MS can be either +1/2 or -1/2. Conventionally, because we use an upward arrow, we usually use +1/2. If you have a spin-paired orbital, like this, right, so this is spin-paired, right, and this is half-filled. In a spin-paired orbital, MS can take on two values. It can be +1/2 or -1/2. Now conventionally, the upward arrow, we just indicate +1/2, but it doesn't imply clockwise or counterclockwise. It just means that if this is clockwise, then this is counterclockwise. Or if this is counterclockwise, then this is clockwise. Right? So if this is counterclockwise, this is clockwise. If this is clockwise, this is counterclockwise. That's literally all that it mentions. But if you see an orbital that has both of these values, that means that the orbital is spin paired. Okay? So the magnetic spin quantum number just shows you if the orbital is empty, half-filled, or spin-paired, right? And we can kind of combine all of this together. We can combine all four quantum numbers, N, L, ML, MS, and we can pinpoint an electron's location. Okay, so let's take a look at an orbital diagram here to kind of demonstrate this. So I'm going to do this with a really small element. Let's do beryllium. Beryllium has an atomic number 4, and let's take a look at elemental beryllium. Okay, so looking at elemental beryllium, this is going to look like 1s2, 2s2 for its electron configuration, right? Let's draw an orbital diagram to demonstrate this. Okay, so this is my orbital diagram here. I'm going to put energy on my y-axis, right? I'm going to start up here. So this is 1s2. Okay, so this orbital is completely spin paired, and then we jump to the higher energy level. This is 2s2, and then this orbital is completely spin paired. Okay, let's say I want to pinpoint an electron. Now there's basically 4 electrons located in elemental beryllium. If I wanted to label each electron, let's say I pick this electron. We'll call this electron 1. Okay, so if I pick this electron, how you can look at its position and thereby its energy, the first quantum number, the primary quantum number, n is equal to 1. It's in the first energy level, right? The second quantum number, because it's in an S subshell, L is equal to 0. Okay, so it's basically like an address book. Just like if you're looking at the address of a person, you can look at their street name and street number, their province or state, right? Their country, and essentially we can abbreviate everything with the postal code, right? We're doing the same thing with electrons. Now the tertiary quantum number here, right, ml here is only going to be equal to 0 because there's only one value of L. It's negative L to positive L. Well, there's only 0 there. And the fourth quantum number, let's say that ms is equal to positive 1/2 because the arrow is going upward. Okay, so these are our 4 quantum numbers. But let's say that we're looking at its neighboring electron. So let's take a look at, let's use a different color there. Let's take a look at this guy. This is electron 2. Okay, first quantum number, primary quantum number, the shell number is n is equal to 1. Second quantum number, the subshell number, L is equal to 0. Third quantum number, ml, can only be negative L to positive L, which is 0. And the fourth quantum number, you can notice here that this is an upward arrow, this is a downward arrow. They have 2 different spin. ms is equal to negative 1/2. So although the first 3 quantum numbers here are the same, right? Oh, sorry. Although the first 3 quantum numbers here are the same as that, the fourth quantum number is different, right? And this brings up a really important concept, and this concept is called the Pauli exclusion principle. So let's take a look at the Pauli exclusion principle. And what the Pauli exclusion principle states is that for different electrons in an atom, not all the 4 quantum numbers will be the same. So although you can have the first 3 or first 2 quantum numbers that are the same, all 4 of them cannot be the same. That's what Pauli exclusion principle states, right? That each electron in an atom has a unique address in terms of its quantum numbers. So you want to think about these quantum numbers as an electron address book. And by using this address book, we can pinpoint the position of an electron, and we understand that position is associated with the energy of that electron. Right? So that's the idea. Okay, let's construct an orbital diagram for carbon 6 and write out the quantum numbers for electron 5, electron 6 in the valence shell. Okay, so carbon 6, we use a periodic table here. Let's write out the full electron configuration. And the full electron configuration tells us where all the electrons in an atom are located. So the full electron configuration, if we use the periodic table, I'm going to put helium back here, right? And you get 1s2, right? Then 2s2, and then 2p, p1, p2, so this is 2p2. Now, if I'm creating an electron a quantum mechanical model to represent the electron configuration, what I want to do here, I'm going to use orange actually, what I want to do here is put energy on my y-axis, right, and I'm going to start off with the 1s2 subshell. Now we have to fill from lowest to highest, so the direction of filling here, this corresponds to Aufbau principle. Okay, so it's important to note these principles. Okay, so this is Aufbau principle, and we spin pair the s subshell in the first energy level, then we move to the s subshell in the second energy level. So we also spin pair this as 2s2. And then we jump to the p subshell. Okay, so this is 2p2, and we have to half fill orbitals before spin pairing, according to Hund's rule, right? So that's what I'm employing here. This is Hund's rule. We always half fill orbitals before spin pairing, and that's what we see there. Now let's pick electron 5 and electron 6 here. Let's call this guy electron 1, electron 2, 3, 4. Let's call this guy 5 and 6. Okay, they're the electrons in the valence most shell. These are probably going to be the highest energy electrons, right? So if I look at electron 5 here, and I wanted to write its address book, it's located, the primary quantum number, the shell number, n is going to be equal to 2. The secondary quantum number, the subshell number, L is equal to 1 because it's in the p subshell. So this indicates that we're in the 2p subshell. And the tertiary quantum number will tell us which orbital you would find this value of L, right? So in this case, because L is 1, ML can take on values from -1, 0, and +1, right? So it's always -L to +L. Right, so this is -1, this is 0, this is +1, right? So ML here, because the electron's located in the -1 orbital, we write -1 here. Okay, so it's found in this orbital particularly. So that's what the secondary quantum number is really useful for, right? Because we find that the electron's located in this orbital, we're going to use this value. Okay, so ML is -1, and then we look at the fourth quantum number, and the fourth quantum number here. Continue with green here, but the fourth quantum number MS, let's say it's +1/2, and it should only have one value, right? Now let's compare this with electron 6 here. Let's do this in, let's use a different color. Let's use red here. Okay, this is electron 6. I'm just going to show that out here. So in electron 6, the first shell number, the first quantum number, primary quantum number, n is equal to 2 again. Second quantum number, L is equal to 1 because we're in the p subshell, so this indicates the 2p subshell. But you can see that your orbital number, ML, your tertiary quantum number, is now going to take on a different value because now we're in this orbital of your subshell, so ML is 0. And the fourth quantum number, it should have about the same spin as electron 5, so MS is equal to +1/2. Okay, so this is really important, right? But you would notice that if you took an electron, let's say we had an electron from this orbital, right? This is from the 2s orbital. Both of these cases, right, they would have the first same three quantum numbers. N is equal to 2, L is equal to 0, ML is equal to 0, but the fourth quantum number can be two different values, right? You can have +1/2 and -1/2. Okay, so because all four quantum numbers will not be the same, this indicates the Pauli exclusion principle. So it's important to understand these three rules: Aufbau principle, where you fill from lowest energy orbitals to highest energy orbitals, and subshells and energy shells; Hund's rule, where you half fill before spin pairing; and then Pauli exclusion principle, which states that no electron in an atom can have the exact same four quantum numbers.